That's quite enough of terminology. Let's get to actually doing something. We'll start with a simple example and try to describe a categorical variable. Suppose you ask 50 people to pick which of the 3 colors they like best from among green, blue, and red. So I'm not saying ask them what their favorite color is, because they'll tell you purple or mauve or whatever. Just ask them a simple question, green, blue, and red. Which do you pick? And make them pick one. And then your data might look like a string of blue, red, red, green, red, etc., etc., etc. Your variable is categorical, and you will have 50 values, each of which is either red, blue, or green. And even those 50 values are a bit of a pain to look at. So a natural thing to do is simply count how many of each kind you've got. And that gives you a little table. So you have the color and you have the number of people that picked that particular color. So you have 50 people in all, and your table says, after you've done the counting, that 30 people picked red, 10 people picked blue, and 10 people picked green. Now that little summary already tells you a great deal about the people's preferences. First, it contains all the data that you had, except you have lost the order in which they appeared in your observations, and you've probably lost which person picked what. But you can see that this group likes red. They were picking red much more often than the other colors. The other colors they were picking about equally. They're split between blue and green, the other people, but the bulk of the people pick red. Now this information becomes much more vivid if you describe it in a picture. And here's a common way of graphically describing such a variable. You've seen it before, I'm sure. It's called a bar graph. Here we go. Easy enough to understand. You have 3 bars, one for each possible value of your variable, red, blue, and green. And the height of the bar is on the vertical axis. And that shows the number of people. So you can see the height of the red bar is 30, the height of the blue and green bars, each of them is 10. So that represents your data. So what I like to do is I'd like to look hard at the axes of this figure, because we are going to use this idea to do summaries of quantitative variables, and there it will help to have examined this picture carefully. Let's look first at the x-axis. Do you see one? Well, sort of, but it's not really an axis, is it? There's no line joining here, and that makes sense because there really isn't an order. There's no number line there. There are these 3 bars that I chose to put in the order red, blue, and green, but I could just as easily have chosen blue, red, and green, and this picture carries the same information. I'm free to draw this if I want. So the values on the horizontal axis have no particular ranking relative to each other. You know this about categorical variables. A number of things on the horizontal axis are up to my discretion. For example, the space between the 2 bars. This one and this one. That's up to me. And the width of the bars is also up to me. So I have a lot of power here. I can do this diagram pretty much however I want. And you know, power corrupts. And so I might go completely wild and crazy and do something like this. I really shouldn't have done that. I really shouldn't have done that. It is true that it is up to me to choose the widths. But you can see from this picture that it is very disturbing to have the green bar be much wider than the blue bar. Because now looking at this picture, you get the sense that many more people picked green than blue. Because what your eye is picking up is not just the height of the bar. The heights are equal of these 2 bars. But it is also picking up that the green bar is wider. It is picking up a combination of height and width. In fact, it is picking up what combination? That's right, it's picking up the area. It's picking up height times width as being big. And this picture is giving you a misleading sense of what the data was saying. Do not do this. It was a very silly thing to do. go back to our old friendly diagram by recognizing that the area of the bar is visually important. That's what looks big. And so by keeping the widths of the bars equal, you're ensuring that not only the height, but also the area is proportional to the number of people in that category. And this observation is going to be really important when the x-axis represents a numerical variable. So let's go back to our comforting correct bar graph, which has been drawn sensibly. And now take a look at the vertical axis. We spent a lot of time talking about the horizontal axis. Let's take a look at the vertical axis. A simple vertical axis just tells you how many people. Do we actually need it? What would happen if we just were too lazy to draw it at all? Well, let's see. Focus on the diagram on the left, this one. Ignore the one on the right for a second. This, you will see, is the same diagram that we've had before, slightly skinnier bars, but the same diagram, but with no vertical axis at all. But even without that vertical axis, it is apparent, you can see clearly, that the number that shows green was equal to the number that shows blue. And you can also see, with a little bit more effort, that 3 times as many people picked red as picked blue. And if you have any doubts about that, look at the picture on the right. What I've done is I've stacked up a copy of the blue bar in the middle of the red bar, and then I've stacked up a copy of the green bar on top of that second blue bar, and look, your 50 people, the total number of people, have been divided into 5 equal bits. 1, 1, 1, 1, and 1, 5 equal bits. The green bar represents 1 of the 5, the blue bar represents 1 of the 5, and the red bar represents 3 of the 5. And so these 3 bars, you can see, just visually, are in the ratio 3:1:1. And that is a useful observation, because that is telling me that this green bar represents 1/5 of the data. This green piece is 1 of the 5 equal pieces. So this green bar represents 1/5 of the data, the blue bar represents 1/5 of the data, and the red bar represents 3/5 of the data. And so you already know the proportions, and you didn't need a vertical axis. You can see by comparing the sizes, the areas of the bars. And so let's write that down. Even without the vertical scale, you can compare areas, and you can clearly see that the colors red, blue, and green appear in the ratio 3:1:1. And so you can think of the data being split into 5 equal pieces, 3 of which are red, 1 blue, 1 green. And in other words, you have this table. Colors are red, blue, and green as before, and now you know the proportion of people in each of the categories. And once you know the proportion, 3/5, 1/5, and 1/5, then equivalently you know the percents, 60%, 20%, 20%, and all of this without the vertical scale. You do not need the vertical scale to do this. What's the information in this table? It is almost all the information that you had in our original table. Our original table said 30 people liked red, 10 people liked blue, and 10 people liked green. This is the same information in percents. What we've lost is that there were 50 people in all. But other than that, we have everything without the vertical scale. And this leads to an important observation, which is that the bar graph, the sizes of the bars, depend on percents, not on exactly how many, not on counts, but on percents, so the count relative to the total. So that bar graph would have looked the same if you had started out with 300 red, 100 blue, and 100 green. Indeed, it would have looked the same had you started out with 4,800 red, 1,600 blue, and 1,600 green, rather strange numbers, but in the ratio 3:1:1. As long as the percents are 60%, 20%, and 20%, the bar graph will look exactly the same. Apart from the numbers that you are placing on the vertical axis, the picture will look the same.